Welcome. This is the first of a three-part video lecture series involving nonlinear force deflection models for planar rigid body mechanisms. So the first one, we're going to talk about how this topic is relevant to your semester project and also go through the fundamentals of kinematics. The second video will address how do we evaluate the number of degrees of freedom in a mechanical system. And then finally, we're going to take a look at mechanical advantage and finally bring everything together to develop some force deflection models. So why learn kinematics and force analysis? In your semester project, you're designing a suspension system, including the geometry of the trailing arm, where the spring and damper is attached to the trailing arm, and also a detailed spring design. These design decisions that you're making influence the relationship between the force at the tire contact patch and the deflection, the vertical deflection of the tire as the suspension compresses. So there's a representation of the vertical force at the tire contact patch. And one question is, given a certain amount of force at the tire contact patch, how much will the suspension move up vertically? So we're going to quantify that. Deflection is delta t, and that's going to be a function of the vertical force. Now, if we think about this without looking at the suspension, but imagine pushing on the bottom of the tire and you apply some force and it moves, so that's going to behave like a spring. It has some apparent stiffness to that, and that's going to be the derivative of deflection with respect to force. So one important question to address here is, does this stiffness, this derivative, depend on suspension position? Or in other words, as the suspension moves through its travel, does the apparent stiffness change? Answer is yes, definitely. As the suspension compresses, the spring angle changes, the relationship between the spring and the vehicle body and the trailing arm, all those angles change. And because those angles change, that's going to change the force relationships in the system, if you think about the free body diagrams involved. And with the change in these force relationships, the apparent stiffness will also change. One way of conceptualizing this change in stiffness is to look at the force deflection curve of a system like this and observe that this curve is nonlinear. So you are accustomed to seeing linear spring force deflection curves where there's a line instead of a nonlinear curve, and the line has a constant slope. But in a more complicated system that has some way of exhibiting nonlinearity, we will have a curve instead. So what we need to be able to do for your design project is take a given suspension design, including the linkage geometry and the design of the spring, and predict for that design the shape of this nonlinear force deflection curve. If we have that shape, then we can evaluate whether that design is appropriate. So why is this force deflection curve nonlinearity important? Now, in this project, we're focusing in on just the suspension design, but it's part of a larger system. And the vehicle level design decisions need to be made such that we get overall good vehicle performance, including the overall suspension performance, things like ride, how comfortable is the vehicle, handling performance, dynamic stability. And these decisions are going to be based on some kind of models. One example model for a suspension is the quarter car model, where we just look at a single suspension assembly. We have several important components. We have the sprung and unsprung masses. The top mass is the sprung mass. The mass below that, that's the unsprung mass. And between the sprung and unsprung masses, we have the stiffness of the suspension and the damping of the suspension, modeled here using a linear spring and a linear damper. Now, the stiffness and damping that is below the unsprung mass, that represents the stiffness and damping of the tire. And as this vehicle, this model of a vehicle, moves to the right, it's going to encounter varying road elevation, and that's a disturbance to the system. And we want to design this system both so that we can reduce the effect of the disturbance on the sprung mass, so a more comfortable ride, and also we want to have nice properties between the tire and the road so that we can improve handling properties. Now, one big assumption that we're making here is that the overall vehicle dynamics are going to be desirable if we achieve an effective suspension compliance that behaves as a linear spring with a specific value, case of be an effective stiffness. And we're assuming that vehicle level designers have made this decision about what this stiffness value should be, and based on their overall vehicle models, with this value, they can say that we're going to get good vehicle dynamic behavior. So now our job is to come up with a suspension design that can come close to approximating a linear spring with this particular stiffness value. So if we look at the force deflection curve again, we are specifying this desired force deflection behavior as this line with slope k sub e. And to make sure that we are close, that we approximate this line, we're drawing upper and lower bounds above and below this line. And so the way we are defining this problem is that we want to design a suspension system such that its force deflection curve stays within this yellow window. And if we look on the right, we have this delta max value. That's a specified value of the maximum suspension deflection. And behavior after that doesn't matter in this design problem. We just want to make sure in this window between 0 and delta max that we stay between the upper and lower bounds. Now, if we're thinking about a model of the actual suspension, we could still use this quarter car model, but instead of having a linear spring, we could replace it with a nonlinear force deflection curve, and this nonlinear spring would more accurately represent the dynamic behavior of the suspension. So one question we should ask is this assumption of linear stiffness valid? So we are going to operate in this project with the assumption that as long as we stay within this window, we are okay and the design's going to work. So that's what you need to focus on. You might recall earlier in the semester, we talked about the difference between linear and nonlinear dynamic models. And one example we looked at was a simple pendulum. And this is a nice way of visualizing the error that can come from neglecting nonlinearities. So if you think about the simple physics model of the pendulum, if you want to linearize it, it involves an assumption that the sine of an angle theta is approximately equal to theta. Well, this is true for very small angles. And if we take a look at the response of the linear model and compare it against the nonlinear model, and if we keep the angles of deflection small for this pendulum, then the error is really small. And that's what the top animation is showing. If you see the difference between the black pendulum and the gray pendulum, there's just a little bit of error. And we can also see how the pendulum height and velocity are being tracked in the plots to the right, and we can see just a little bit of error there. Now, if we look at the bottom set of animations, this shows the exact same pendulum, exact same linear and nonlinear models, but in this case, we have much larger deflections, and we can see that there's a huge error between the linear and nonlinear models. So if we have large deflections with the pendulum, then we do need to account for nonlinearities. So is this assumption of linear stiffness valid for the pendulum? It's not valid for large angular motions. For suspension, it's not valid for large vertical deflections. We can't just assume that we're going to get linear behavior. So what we're doing in this design problem is modeling the nonlinearity, but making a design requirement that even accounting for this nonlinearity, we are going to get a force deflection curve that is approximately linear. Okay, so we're assuming if the more accurate nonlinear force deflection curve stays within the specified yellow window, the effects of nonlinearity on the overall system behavior will be small and desirable vehicle dynamics will be achieved. The window is based on this equivalent stiffness I mentioned and an allowable force deviation and a maximum anticipated suspension deflection, sometimes also called the rattle space. So what if we wanted to use a more accurate design process? If we wanted to use more accurate models, well, we could simulate overall vehicle dynamics using a fully nonlinear model. And there may be some potential with this additional design freedom where we could exploit the nonlinear characteristics of the suspension system to improve overall system behavior. But one big drawback of this, of course, is that it generally is more difficult to use nonlinear models in design, and that's really outside the scope of this course. So we're making the assumption of linearity, but we need to validate that using a nonlinear force deflection curve and make sure that we're within these bounds. All right, so to evaluate a given suspension design, one that you might propose, we need a model for predicting this force deflection curve. And it needs to predict the force at all deflections between 0 and the maximum deflection, not just at a single point. So we need a very general model. And this is a nice example of developing a model that is appropriate for design. It not only needs to accommodate any appropriate level of deflection, it also needs to accommodate changes in physical system design. So if we change the geometry of the suspension linkage, then we need a model that can accurately predict the force deflection curve given those changes in design. Now, with that in mind, let's look at how this relates to your project deliverables, at least the first couple. In project deliverable number 1, your job is to derive this force deflection relationship that will then later be used for evaluating suspension linkage designs that you propose. So in the first deliverable, there's no design, it's just an analysis problem. And we're going in class to walk through at least an outline of how to derive this relationship. And we're also going to go through MATLAB code that you're going to be using for this. There are pieces of the MATLAB code that are what we call protected code. They're hidden, you can't see them. You can use them for validation, but your job is going to be to derive what's behind those hidden pieces of code. But then you have this MATLAB code that you can use to check. So you have the known solution, and you can very easily see if you got the right derivation. So project deliverable number 2, this is where you take the model that you created for project deliverable number 1, and you actually do design. You can iterate on your design and use your model to see if your suspension falls within the required window. You're going to be designing the suspension linkage, and also you're going to be specifying a spring stiffness that will then, so the stiffness of the actual spring being used in the suspension, that then will meet requirements that gets us this desired equivalent stiffness, and we fit the whole curve within the yellow window. One thing that most groups discover is as you proceed with later design steps, such as designing the actual physical spring, or maybe designing the structure of the different components like the control arm, you might have to go back and revise your overall geometric design of the suspension linkage. For example, if you have a spring design that achieves your desired stiffness, K sub S, what if there's just not enough space for it to provide enough deflection to get all the way to delta max? So with the helical compression spring, as we'll see later on in class, there's something called the solid length. Basically, if you compress the spring until all the coils touch, that's the smallest it can be compressed, and that's a constraint that you're going to have to work with. So if that solid length is too big, to allow your suspension to reach delta max, then you're going to have to go back and adjust your design. But that's going to be easy to do if you have this nice MATLAB tool that really quickly evaluates the behavior of your suspension design. So besides this project, how else might this knowledge be useful? It helps to understand how to analyze and design more general mechanisms. Often it's very helpful to be able to come up with elegant solutions to engineering problems where we use passive components such as mechanical components to solve some kind of engineering problem. So here's one interesting example, this Sylvester-Kemp mechanism that allows a nice linear translation of the top yellow piece using this rather complicated mechanism. Another example with interesting kinematic and dynamic behavior is a passive walker. It's designed such that just from gravitational potential energy, this walker is capable of walking down a ramp with no additional motion. And here's strobe images from an actual passive walker. Another example of an interesting mechanism design that involves kinematic and force analysis would be this constant force gripper, where the basic idea is we want a mechanism that is capable of grasping a wide range of different sized objects, both soft and hard objects, but it approximately applies the same force to this object. And the plots on the right-hand side show how for different size objects, we're able to get an approximately flat curve toward the right of the figure. For this video series, and more broadly for the associated assignments, the learning objective for you is to learn how to design a planar mechanism that exhibits desired nonlinear force deflection properties using nonlinear kinematics and force models that you have derived. So the video series focuses primarily on how to derive the model. In class, we're going to talk more about design. How do you design using this model to achieve some target properties? So you can think of having some target force deflection curve you want to achieve. This is kind of an open-ended problem if you want to design a mechanism that produces this desired force deflection curve. There are several steps that are required to build up to this objective. We're going to go through some of the foundational knowledge that you need in this video, and then in the next two videos, go through several more examples that will build up the understanding that you need to derive the model that you need for project deliverable number 1. Okay, we're going to talk about kinematic analysis first. You've probably encountered this term before. We're going to go through a few quick definitions. What is kinematics? It's a branch of classical mechanics that describes the motion of points, bodies, and systems of bodies without considering the forces that cause the motion. It's all about motion, not about forces. It's the study of geometry of motion. So you've certainly seen some kinematic analysis before. Where did you see this? In a first course in engineering dynamics, usually students will learn some type of kinematic analysis of different kinds of mechanisms. So here is an example homework problem from a textbook that has been used for first course in engineering dynamics. What we see here is a robot. We're only looking at the planar motion in the XY plane of this robot. And it has several links, and we have 3 joints defined, A, B, and C. These are pin or revolute joints, meaning they can only rotate about the z-axis that's coming out of the page. And we're asked here, we're told that the link AB, it's rotating at a particular speed in a particular direction. We're told what link BC is doing as well, and we're told how link CD is rotating. Now, we have this definition of all the velocities for each of the joints, but we might really be interested in, well, what is the velocity with respect to an inertial reference frame of the end effector at point D? So how do we calculate that? And this is pretty typical of the type of problem that you might have seen in a first course in engineering dynamics, where you answer this kind of question for one particular configuration. But one of the challenging things to have to wrestle with here is coming up with a model that's capable of answering questions like this for any particular position, any possible position the mechanism can be in. So with this typical kinematics problem, we're given a specified mechanism position, known velocities, and we're supposed to solve for some unknown velocity. This is really important to learn how to do, but it has fairly narrow scope and utility, so we want to build on that so we can come up with more general models. We need to address this question, well, what about all the other possible mechanism states or positions? And this is going to have a nonlinear behavior because with a robot like this, we're going to have very large angular deflections. We cannot use small angle assumptions and have an accurate model of the system. Just a couple of notes about terminology that we're going to see in just a minute. With a robotic system like this, we have one way of describing its position as the value of all the joint angles. And that position could be described as a vector of numbers, a vector of all of the angles of each of the joints. So if we have 3 joints, we're going to have a vector of length 3 describing the position of the robot. And what we usually call that is the configuration space. So if we specify the position of a robot with respect to its joint positions, that vector quantity describes the position in a space called the configuration space. The actual physical space, think about where point D is in this physical 3D space, that's what we call the workspace. And we want to be able to map the configuration space to the workspace. So we're going to learn how to derive nonlinear kinematic model, and then by the end of the video series, we're going to learn how to combine that with force analysis. Let's talk about this distinction between kinematics and dynamics. Kinematics describes motion, but it does not involve quantification of forces. So in a general 3-dimensional kinematics problem, such as the robot we saw on the previous slide, we would be interested in mapping a quantity in the configuration space represented by the vector q to a point in the actual physical workspace represented here by the vector p. And so there's some vector valued function or mapping from the configuration space to the workspace. Deriving this function f, that's one of the challenging tasks in kinematic analysis. Now, another thing that we would be interested in is mapping velocities in the configuration space. So for example, the angular rotational speed of joints for the previous robot and mapping that to uh, velocities in the workspace. And the way we do that is using what we call the Jacobian. It's a matrix, but one of the key observations here is that the quantities in this matrix depend directly on the position of the robot, and that's described using this vector Q, the configuration space. So J, this mapping depends on position. This is a very nonlinear relationship. Now, if we are moving on to talk about dynamics of mechanical systems, here is where we start to quantify forces that are associated with acceleration of inertias. So you're familiar with Newton's second law, either in translational motion or rotational motion, where the force applied to an inertia or mass will result in a given acceleration. We are also interested in multi-degree of freedom dynamics problems. And if that is the case, then it's possible to derive matrix-based differential equations that look like what we see in Newton's second law. So here's a general robotics model that includes dynamics, and there are several components to it. On the left, we have the inertia term with the inertia matrix. And notice that the inertia matrix, it's sort of like the mass matrix that we've seen before when we're looking at torsional vibration. It depends on position, Q. It depends on the state of the robot. It, of course, depends also on the design of the robot. And then that is multiplied by the acceleration of Q to give us the inertia term. And then the second term that gives us the centrifugal and Coriolis terms, that depends on the position and the velocity in the configuration space. And then the third term, that is the gravity term, that depends on positions and design. And then on the right-hand side, we have the forcing vector. So if we had an actuator, say a motor, at each of the joints, then we'd have some kind of time-varying trajectory for each one of the elements in the torque or force vector on the right-hand side. So key takeaway, kinematics focuses on motion. Dynamics brings in force analysis that's associated with acceleration. So in this semester project, how are we going to treat dynamics? In a real suspension, the components have inertia. And as the suspension moves, as it is compressed or as it rebounds, these components are going to experience acceleration. And because of this acceleration, there are going to be forces associated with that. In this project, we're going to make a number of simplifying assumptions, including that the dynamic forces from accelerating suspension components are really small compared to the other forces in the system. For example, the spring force in the suspension system. We're going to assume that is far larger than the forces due to acceleration of the suspension components. Or the inertia of the sprung mass is much larger than the inertia of the unsprung mass. With that assumption that these forces are small, we're going to neglect rigid body dynamics in the suspension, and we're going to assume that this simplification is not going to result in significant error in predicting overall vehicle performance. We're also making this assumption I've stated before that if we meet the requirements for the force deflection curve, namely that it stays within this yellow window, that we are going to have good vehicle dynamics. And that is a pretty big assumption. If you were designing an actual vehicle, really you should simulate the vehicle using a full nonlinear model. Some additional assumptions. We're doing what we might call a quasi static suspension analysis. In essence, the accelerations we are treating as approximately equal to zero, but we are very interested in, well, what are the forces, the nonlinear forces involved in the system as the suspension moves through its travel. So this quasi-static analysis means we're assuming we're moving the suspension slowly, and so we can neglect the effects of acceleration on forces in the system. Another big assumption is we were restricting this to planar motion. We're only dealing with planar kinematics. That really simplifies things. For those of you who are interested in learning more about three-dimensional kinematics and dynamics, I would recommend that you consider taking a first course in robotics that really digs into the different types of models you can use for three-dimensional kinematics and dynamics. Okay, next topic we're going to introduce is these concepts of kinematic chains and mechanisms. First, a kinematic link is a rigid body, meaning it's something that we assume does not deform, that has at least two nodes that we can connect to other links. So here we have links with 2, 3, and 4 nodes. And of course, this assumption that there's no deformation, that's a very ideal assumption. Any real physical body is going to have some kind of deformation when you apply a force to it. But here we're going to assume that deformation is extremely small compared to the motions of the kinematic links that we are interested in. A joint or a kinematic pair is a connection between two or more links that permit some relative motion between the links. Usually these joints will impose some kind of constraints on what kind of motion is allowed. One example of a joint is a revolute joint or a pin joint. It allows rotation only about one axis of rotation. So some examples of a revolute joint would be on the human body, a knee joint or an elbow joint. And to the right, we have a couple of images depicting revolute joints. There are a few different types of motion to be familiar with: rotational motion, translational motion, but we could also have complex motion that's a combination of translation and rotation. There are several different types of joints to be familiar with, and each of these has its own number of degrees of freedom. And when I say degrees of freedom, that corresponds to the minimum number of parameters, quantities that are required to define the relative positions between the links in this kinematic pair uniquely. All of the examples on the top are what we call full joints. These joints constrain all degrees of freedom except for one. A revolute joint on the left, that allows just rotation. A prismatic joint, that allows just one type of translation. A screw, that involves complex motion, both rotation and translation, but it has only 1 degree of freedom. It requires only one parameter to fully describe the positional relationship between the associated links. Half joints allow 2 degrees of freedom. So in this example, this cylindrical joint, we can have both rotation of the cylinder, and we can also have translation of this cylinder moving in and out. The next joint is a spherical joint that has 3 degrees of freedom. So in the human body, this is similar to a shoulder joint or a hip joint. Finally, a planar joint allows 3 degrees of freedom, 1 rotational and 2 translational degrees of freedom. Here are a few additional types of half joints that are important, and actually one of them you're going to see in your homework. On the left, we have a link that's up against a plane, and we call this a force-closed joint because it relies on force between the link and the plane to maintain contact. So in this case, we have 2 degrees of freedom. We can have translation back and forth and rotation of the link. Now, on the right, instead of relying on force to keep contact, we have a pin inside of a slot. And so this is a form-closed joint. It's constrained to stay in the slot. But again, we have both translation, back and forth, left and right, and then rotation of the link because the pin can rotate in the slot. Another thing to be aware of are higher order joints. This is where we have more than 2 links connected using the same joint. The order of a joint is the number of links connected minus 1. So in these previous examples, we had 2 links connected. So 2 minus 1 is 1. So those were first order joints. Here we can see an example of a second order pin joint on the right. We have 3 links connected at the same joint. Let's talk about mechanical degrees of freedom. I've used this term already. Let's look at how many degrees of freedom would a rigid body in 3-dimensional space have. So we assume that the particles in this body cannot have any relative motion, any motion relative to each other. Everything moves as a rigid body. But one way of describing the ways we can move this body is as 3 translations, x, y, and z, and 3 rotations, theta, x, y, and z. So we have 6 total degrees of freedom. If we have a quantity for each one of these degrees of freedom, we can completely and uniquely describe its position. And for a rigid body in 3-dimensional space, the minimum number of quantities required to describe its position is 6. I mentioned before that joints remove degrees of freedom. They restrict the ways in which a rigid body can move. A 6 degree of freedom 3D rigid body, if we were to have it up against a plane, that planar joint is going to remove 3 degrees of freedom. It prevents 2 types of rotation, and it also prevents vertical translation. So the only 3 degrees of freedom left are 2 translation and 1 rotational degree of freedom. Here's another example, another way of looking at this concept of joints removing degrees of freedom. Here I have sketched out 2 node links, and each of these, if they are in a plane, have 3 degrees of freedom. We can describe their position uniquely using 3 quantities. So link 1, we have x1 and y1 and theta1 that completely describes its position. And then with link 2, we have x2 and y2 and theta2 completely describing its position. So what happens if we link these 2 together with a pin joint or revolute joint? How many total degrees of freedom does the system have? In this case, adding the revolute joint removes 2 degrees of freedom. Here is just one possible way of defining the position of this system. We could define the translational position of the revolute joint, x1 and y1, and we could define the global orientation of link 2 with theta 2, but then we could also define a relative position between link 1 and link 2, this theta relative. So we have 4 quantities that are required to describe completely, uniquely, this system in space. So keep this in mind. Make a note of that adding a revolute joint removed 2 degrees of freedom. In the second video, when we look at quantifying the number of degrees of freedom in a mechanism, this will show up again. So revolute removes 2 degrees of freedom. Okay, so we've defined what kinematic links are, what kinematic pairs or joints are. A kinematic chain is an assembly of links and joints connected in a way that provides a desired output motion for a given input. So shown in the sketch here is an arbitrary kinematic chain. We have multiple links connected using multiple joints, and actually not all of the degrees of freedom are identified here, just the relative degrees of freedom. We would also need to have at least 3 additional quantities to completely describe the position of this kinematic chain. So joints connect the links and restrict motion in different ways. There is relative motion allowed between the links for this to be a kinematic chain. Otherwise, if there was no relative motion allowed, we would have a structure. Now, the difference between a kinematic chain and a mechanism is essentially just grounding one of the links. A kinematic chain with at least one grounded link is called a mechanism. Here are some additional definitions. We might be interested in open or closed mechanisms or kinematic chains. So an open mechanism is shown on the left, or a serial mechanism, and then a closed mechanism is on the right. If we note that both of these grounded links, bottom left and bottom right of the image in B, those are connected to the same ground. And so that's essentially one link right there. And this forms a loop. And so if we have a closed mechanism, we will see loops in the topology of that mechanism. Here are a few examples of open or serial mechanisms. One is a serial robotic manipulator, and another is protein folding. So at the molecular level, different parts of the molecule are allowed to rotate relative to each other, but the angles are constrained. And proteins can fold up by using these rotations. This is a serial mechanism as well. Here's an example of a closed or a parallel mechanism. Here's a delta robot where the end effector is in the middle at the end of the 3 links in the middle of the structure. And as we move the outer ends of the links up and down, we can change where the end effector is. And because it's a closed system compared to an open system, these generally have greater structural rigidity. Another type of kinematic chain topology is a tree. Here is an example of a model of a human body, kinematic model of a human body, and that is a tree. We can depict it as a graph that is a tree. A graph that's a tree is one that is fully connected and has no cycles or loops in the graph. Okay, to summarize part 1, we discussed the relevance of force deflection models for planar mechanisms to the semester project. You need to learn how to derive force deflection models for planar mechanisms. We identified that large motions require nonlinear analysis, and we also discussed techniques that go beyond what's typically covered in a first course in mechanical dynamics. In the past, you've probably only seen cases where you're interested in analyzing kinematics when a mechanism is at one particular position, but we need a more general model than that. We defined kinematics in related terms and made a distinction between kinematics and dynamics. We discussed joint, link, and mechanism types. Later on in parts 2 and 3 of this video series, we're going to learn how to calculate degrees of freedom in a mechanism and also how to derive complete force deflection models. Thank you.